Good morning, everyone, and welcome to the last day of the virtual VGEM 2021 workshop. So today we will start with some exciting tutorials, and I will let our student representatives, Agnit and Mei-Yun, to introduce themselves and the speakers.
Hi everyone, my name is Mei-Yun. I'm a fourth year PhD student in University of Illinois. Today I'm the QA moderator of the student invited plenary session. I'm here to introduce the Agnit. He's going to be the introducer of this plenary session.
Thank you so much, Mei-Yun. Good morning, everyone. Hello, my name is Agnit Mukhopadhyay. I'm a fifth year PhD student at the University of Michigan. Along with Mei-Yun, we are also the student representatives for the GEM student community. And today we are honored to introduce Dr. Ferdousi as the student invited plenary tutorial speaker. Dr. Ferdousi is currently serving as an assistant research professor in the Institute for the Study of Earth, Oceans, and Space at the University of New Hampshire. Her current research focuses on the understanding of magnetosphere-ionosphere-thermosphere coupling using first principles-based modeling approaches and data-driven methods. She is the PI of a NASA LWS grant that looks at modeling the response of geomagnetically induced currents using sun-to-ground modeling. She is also co-PI of an NSF GEM grant on understanding connections between Earth's magnetotail and ionosphere through imaging. Dr. Ferdousi holds a bachelor's degree in physics from the Islamic Azad University in Iran and has also received a master's degree in high energy physics from the Southern Methodist University in Texas. She obtained her PhD degree in the Department of Space Plasma Physics from the University of New Hampshire in 2017. She was advised by Professor Joachim Rader, whom we heard yesterday, and her thesis was on the study of magnetotail dynamics and their ionospheric signatures using the global model OpenGGCM. Dr. Ferdousi is an established researcher in space sciences and an expert on numerical modeling approaches in our community. Along with her current position at UNH, she's also a domain researcher for the NASA Frontier Development Lab, working on understanding the geoeffectiveness of solar storms. She's also an active collaborator of the Artificial Intelligence Data Analysis Team and the Center for the Unified Study of Interhemispheric Asymmetries, or CUSIA, Drive Center. Today, Dr. Ferdousi will be talking about machine learning in space physics. Please join us in welcoming Dr. Ferdousi.
Thank you so much, Agnit, for the introduction, and thank you so much for giving me the opportunity to give the student invited talk. This is such an honor for me, especially I was a student a couple of years ago at GEM. So let me share my screen. When Agnit and Mei-Yun asked me to give a talk, they were wondering how they could apply machine learning to their studies. And most of the students now are interested to get their hands on machine learning. So I thought I would give some basic of machine learning, also some examples that I was involved on them, as well as some history of machine learning. We already had machine learning in our field a couple of years ago, what happened back then, and why we think now is the golden time to do the machine learning. So let me begin my talk with machine learning is bring the news to you. Machine learning is just nothing more than fancy statistic. So if you're already using data analysis, and if you're already using some programming language like Python or IDL to do your visualization and do data analysis, and you have basic understanding of statistic, you're on the right track. Usually when we have, when we use data analysis, we have some functions, some data, and we can identify the single distribution with simple analysis. But Now imagine that you have distribution that is function of two distribution. With simple analysis, it's hard to distinguish between these two functions, and it's complicated to get this distribution like correctly. But with already developed machine learning tools like unsupervised learning for clustering, for classification, clustering actually, and supervised learning for clustering, you can easily do these tasks. So why now? Why like everyone is talking about machine, all of a sudden about the machine learnings? We are at the time of big data. Data is produced every 15 seconds. This might be old, might be more than 15 seconds. We produce 2 gigabytes of data. It's from satellites, from like our simulations, and this is in our field. But now imagine like everywhere. There are data everywhere, like in Netflix, in Amazon, and everyone is trying to sell us something. At the same time, we have the development of GPUs. GPUs are the main tool now that machine learning experts are using. And we not only like own to like machine learning, like, you know, development of GPU, it's been coincidence with the Bitcoin data mining. Lots of data miners now are using GPUs. So companies like NVIDIA put lots of their effort on creating more powerful GPUs. At the same time, like companies, high-tech companies like Google, Facebook, Amazon, Wayfair, they're producing lots of data. And for that, they need to use their data. So they're not only investing on the tools, on the models, they are also training humans to do more machine learning. And so as Compreal 2019 brought, so all of these things and now is happening at the same time. So now let's go back and see when machine learning in our field started. I was in a conference a couple of months ago, with Bala Podawal, and Bob McFerrin was there, and he was talking about how they use neural network and artificial intelligence back in 90s. So I emailed him, asked him for more insights, and he kindly emailed me back, and he said around 95, Nelson Maynard from Air Force asked him to investigate possibility of machine learning in space weather. And he looked for different artificial intelligence, and he found that like insurance company, mortgage company, they're using machine learnings. At the same time, our nearest neighbor, the Sun people, also use machine learning, like Macintosh paper that I'm citing here. They're using machine learning for solar wind prediction. But he was telling by the time that he was using the neural network by his student Tom O'Brien in machine learning was not very accepted in the community and did not have the promising result. So so it was no more funding to continue this work. And he applied different methods closer to neural networks to do the research. I should say this is not a complete list. This is an example. So another interesting thing I found is from Campria's paper. So what he was showing is the number of publication about machine learning in space weather. And as you can see over the years, they have jump and down, but now this is 2018, we have the biggest jump. And I think if we have the data for 2019-20, it's even larger than this. And he was saying we will see in the future if this is a noise or if it's going to stay, but most probably because those three things are happening at the same time, we are on the rise of machine learning this time. So now let me tell you about machine learning techniques. These are just simple, like when we talk about machine learning, there are two main types of tasks are come in place. Supervised and unsupervised learning. The main difference between the supervised and unsupervised learning is that for the supervised learning, we know the ground truth, or in the other words, we have a prior knowledge of the output values for our samples should be. Thus, the goal of the supervised learning is to learn the function that give a sample of data and desired outputs, and the best approximation would be reached between inputs and outputs. And among them, we have classification and regression for the supervised learning, and for unsupervised learning, we have clustering and dimension reduction. And so let me give you an simple example illustration to show how these things work. For example, for the supervised learning, we have sets of data that we label them, and then we know what each of them are. And then we give them through training, through validation, and the output would be the label data that we have is either triangle or circle. Whereas on supervised learning, on the other hand, we do not have labeled output. So the goal is to infer the natural structure present with a set of data points. Now imagine that we give a set of data that it's raw to the algorithm, and we don't know if what are they. And so they go through some algorithm like k-means, SOM, and the outputs, there are two clusters. And based on our knowledge, we know we can call them, there are dogs and cats. So that's the main difference between the two methods. I'm going to give you now some examples of both of them. So unsupervised learning classification using OpenGGCM simulation. This work has been done by Dr. Maria Elena Innocenti. She is a professor at Germany right now. And her aim was to, and you can see her submitted paper is in preprint in Analysis journal right here. And so her aim was to understand the potential of unsupervised classification methods for a large amount of data and in the different magnetosphere region. And the goal was to gain from the simulated data valuable experience to apply the same method to the spacecraft observation. So the reason, again, why she used the unsupervised learning. In unsupervised learning, our data set is not labeled and we don't have bias to different regions. And we might find different things. And the reason that she used simulation, because simulation is a known controlled environment and we can focus on classification rather than pre-processing. Sorry. For the methodology, we ran the OpenGGCM CTIM RCM model that was developed by Jimmy. He had a tutorial yesterday. And she applied dimension reduction when we had the OpenGGCM results. Then she applied training of self-organizing map. This is one of methods of unsupervised learning. And she extrapolated distribution of feature across the nodes to train the maps. And she used classification of trained map nodes into a smaller number of clusters that can be mapped to the magnetosphere regions. And for the validation, she compared different unsupervised clustering, different variables and different trainings of the different feature of the magnetosphere, for example, for velocity or for magnetic field or for density. So she used for different parameters and saw which one gives better clustering. So here is the result. On the top left, you see the the result, this is the raw magnetosphere simulation of OpenGGCN. And then the first one remarks the large scale of magnetosphere region are that we are aware of. What we know, for example, where the plasma sheet is, where the magnetopause is. And then this video shows how the nodes of SOM, only PC0 and PC1, are moved during the feed of the data distribution, as you can see here. Finally, here, she was able to distinguish different clusters. Now focus, for example, like cluster 0, it's a solar wind, I think, and see how these different clusters are distinguished between with SOM. From that, she was able to get different regions of the magnetosphere based on unsupervised learning through different regions of the magnetosphere that we know. Like here is the solar wind, here is the plasma sheath, lobes, and different regions. So we didn't give the machine learning any prior knowledge what are these regions are. And machine learning was able to distinguish between these regions clearly. So the next goal was to see if we can apply the same techniques to spacecraft. This is a work by our great graduate student. He is Andy James Edmond. He is at UNH, he's Jimmy's student. And his goal was to infer the transition region in the magnetopause and the bow shock between for many years of Themis data. And he used K-means algorithm, and he used different parameters from the Themis A data with 1 minute time resolution. From these, applying these K-means, which is hard clustering, we do not tell the data what each region means. He was able to get 3 regions, the orange, blue, and yellow. And then cluster 1 is the magneto sheath, and cluster 2 is magnetosphere, the orange one, and cluster 3 is the solar wind parameter. But just with so the method that he used is known as hard clustering. So we do not assign any label data. But with that method, we were not able to get different transition region like bow shock. And so for that, he is going to apply soft fuzzy clustering. Basically, he is going to assign each points of K tubes of probabilities indicating the confidence of, say, data points. And so with that, he is hoping to develop a model of the magnetopause to include different regions. The next is the work that I, with my colleagues at FDL, developed during the G-effectiveness, in the G-effectiveness team during the 2020 FDL. And our aim was to create high resolution global model of DB and DBDT with predicted time and using machine learning techniques. And we are the challenge that we had with GICs is that the data is not readily available. And GIC, as you probably know, it's very could damage our infrastructure like power grids, pipelines, and rails. And so the next available close to GIC we have is ground magnetic field perturbation that we could use supermag data to have them. So why do we need to create a new forecasting model? We already have the MHD models. We already have the empirical models. What's new? So the current forecasting models are not capable with the prediction that industry requires. For example, for MHD models, to get all those small structures of perturbation, we need high resolution runs. And that is computationally expensive. On the other hand, we have the empirical models that like Weimer, he's doing such an amazing job, and we used his work as a reference. It's based on averaging geomagnetic measurements and solar wind data. In his paper in 2013, he mentions that so because this method is based on averaging, it might kill some of those sharp perturbations that are required for GICs. So that's why we decided to create a new model. So for the data, we used SuperMag data for one day. Our model has two parts. We have one part, we use a spherical harmonic to get the composition of the magnetic field on the ground in Northern Hemisphere. And on the second part, we're using the like forecasting model. For that part, we use this, for this part, we use the SuperMag data above 40 degrees and MHD model as a ground truth to make sure how our model is working. For the technique, we use the lasso regression because lasso gives better representation of dB all over the globe. And so the next step was to validate our model. To validate that model, we run the OpenGGCM model for 24 hours. And here you see the data for that. This is one time frame. And we extrapolated the team SuperMag positions from OpenGGCM data, and we applied our lasso regression, our methods on that. Now we get a new representation of magnetic field perturbation. And as you could compare the ground truth MHD and our methods, we are able to capture most of the regions. Also, in addition, we compare our data with a SuperMag and Weimer model. You cannot easily see here, but most of the perturbations are covered in our model better than, a little bit better than Weimer. So the next step is to develop our forecasting model. To do the forecasting model, we use that SuperMag data that we had with the spherical harmonics. In addition, we used the Omni data for 1 year during the 2013. 80% of our data was for the training and 20% was for the validation. And the sets of parameters that we use, we first fed the model with just raw solar winds, like different parameters like velocity, Vx, Vy, Vz, By, Bx, Bz, and we noticed that our model is not doing great. So we went and checked how Weimer is doing, and we use the same parameters as Weimer did. Basically, instead of giving like Bx, V, Y, Z, we gave total B, plasma velocity, temperature, and clock angle, and F10.7. So, and the next step, we applied deep learning, GRU, graded neural network, as well as multi-layer perceptron from the solar wind to infer the coefficients of spherical harmonics. And those coefficients translate to magnetic field perturbation. So the main difference between our model and Weimer model is our optimization. We use deep learning, and he used other sorts of approximation. Other than our approach is pretty the same. So now we have a little bit of result. This is very preliminary. It's during the St. Patrick's 2017 events. And on the left, you see the Weimer model. On the right, you see our model. And on the very right, you see the SuperMag prediction. And we determined MSE, we trained model for northward component of the magnetic field, and then eastward component of the magnetic field to get the dBH. And this result is for dBH, and these are for the dBn and dBe. As you can see, both of us and Weimer are not doing very well during these particular events. And I noticed with the MHG simulation, we are doing the same for this event. And I noticed in other papers, they have some difficulties with these particular events. And what we noticed that Omni solar wind data for the 2015 St. Patrick's storms are not complete. And next step, we're going to use different solar wind, like from ACE probably, and we are going to enhance our model as well. The other, so the other group is doing lots of great job with machine learning is Magician, and the PI is Hundred Connor with Amy Kissy from UNH and University of Alabama Fairbanks. And they're also studying GACs and using machine learning techniques. For here, they are comparing different deep learning techniques like LSTM and artificial neural network to train the model for Ottawa stations. And what they found is that the LSTM is a little bit more skilled than artificial neural networks. And they have lots of amazing students. They had posters, they had talk in the community, so go and listen to them. In addition to that, Dua Osterk, she is using super darn data to develop a multi-scale ionospheric convection and using MSV multi-layer perceptron. And based on solar wind data as well as the solar wind data, super darn data, sorry. Another job they're doing is they're developing a tool for automatic detection of aurora, classification of aurora using supervised learning based on the poker flat all sky aurora images. So now that I gave some examples, I want to go a little bit beyond like these examples. So what do we need as a community to keep machine learning in space physics? We have lots of data. We have like data from like MMS, THEMIS, and we have simulation data. But when you go to these machine learning workshops, the main things everyone complains is about high quality data. And if you are already doing machine learning, 80% of your time is going to make sure that you have AI ready data sets. And as a community, if we have data sets that are available, so it would be much faster for students to use those data sets. Also, it would be great if we have reproducible models, reproducible adaptable AI models. I know the AI models are data sensitive, meaning models developed for one mission may not apply to another. But if models trained with like test data on the ground may not perform well on deployed in space, adaptable AI models can be trained on historic data, for example, and then be tuned for other missions. And one last thing I think our community is missing is model validation. And this is not only for our machine learning, for our forecasting model, we have the same problem. For now, we use like HSS score or score to validate the models. And those are sometimes very harsh and penalize model if the models saw perturbation like 5 degrees below the supermag observed. So we better to come up with better metrics for the community as well. This cannot be achieved like easily. We need to have like a SIST coordination system, like CCMC, that has all the, for example, models, and then people can go run the models there, and then the data is ready, always available. We need to have heliophysics centralized and standardized community-based infrastructures. And right now, all our studies or our simulations, there are in different paper, different like journals. Some are in the Frontiers, some are in JGR, some are in GRL. It's very hard for people to get all these models. But if we have a coordinated center that we could upload our data and models there, it would be easy to access them. In addition, it's for the future of the mission, automatic operations is really necessary. Right now, some of our missions already doing doing burst triggers. For example, for MMS, cluster and Themis, the memory management usually use burst triggers to get the data points that are most important for the science. And there already has been applied machine learnings in the space as well. So now I want to focus on the resources for hands-on machine learning for students. Because I think this is really necessary. I wish I was a student, so it would give me like a list. It's I know what options do we have. If you are if you would like to stay in academia, I suggest like Frontier Development Lab is very good, because Frontier Development Lab is partnership between NASA and private companies like Google, IBM, NVIDIA, and they would give you lots of resources. And basically what they hired 2 researchers from the domain science and 2 researchers from the machine learning, and they put you in a group, and you basically have to teach each other different things. And because you're on the same level, it's easy to ask like questions, and you just go on the paper and try to explain things together. And the thing is, like, it might be a little bit competitive, but I've seen people like applied many times and got it eventually. And maybe everything in your resume is perfect, but the research for that year they have is not related to your research. So if you apply next year, you probably get it if they have the research related to your work. Another good place is NASA Heliocacticon. It's run by Barbara Thompson. She's doing amazing. She's very hands-on. She helps the students to even install Python in their laptops. And they already have some resources in GitHub that I put it here, and I'm going to post it in chat and Slack. And you can just use and to get some basic idea of different things. They have different Jupyter notebooks there. And if you want to go to industry, I've heard lots of students had good luck with the Insight Fellowship. It's a 7 weeks intense fellowship, and it's for postdoctoral people. Like it's after you have to have your PhD to apply for them. And basically they have lots of industry, and they train the postgraduate students, and it's a bridge between academia and industry. And that's another competitive place, but I know like people applied after a couple of times, they got it. If you don't have time to go through like that 7 weeks, or you cannot dedicate that time, of course, Coursera or LinkedIn Learning is another tool. They have, if you search, there are a bunch of machine learning, data science courses, and you're able to share them on your LinkedIn. So when people search for your, looking for like candidates, they can see what courses you're already taking and what certificate you already have. Another resources I found very useful is AIDA. They are developing a Python package for analysis of spacecraft data and in heliospheric missions. And also from AIDA DB, they have the simulations included on that as well. They also had a school, I think last year, they probably have, yes.
But you have sorry to interrupt you, but you have you have around 5 minutes.
Okay, so I'm gonna finish on time. Another thing is very useful is machine learning statistic book. It's such collection of Jupyter notebooks. You can go there and use those notebooks to do data mining, to do the machine learning. I think for the Jupyter notebooks is because you can just play with things and apply the same techniques to your data set. That would be very useful. Another important resource I really find, like Brian McGarrahan has collected is set of AI ready data set is in his GitHub that I'm going to share with you. Recently there was a article by Jacob Bortnick and Enrico Capriel, and it talks about 10 ways that you can apply machine learning to space science. And I think that's another useful resource that you could have some ideas what techniques are available and which one is applicable to your research. One last thing is Google Data Science Colab. In general, I love Colab because you can share your code with everyone and you can do collaboration easily. And it's free GPU, so you can, like for simple models, you can run the models. You probably cannot train your models there, but you can run the models. And if you go to FDL, they give you free Google GPC, Google Cloud, so you can run the models there. You can train the models on that. Another important things is Helio machine learning white papers that I think is students can get involved with. You can find the link here and I'm going to send it to you. There are a bunch of machine learning papers that you can put your names on there. And at least if you have time, you can just go and listen to them. Believe it or not, 2050 is going to be run by you students, and you have to be involved in, I think, in these white papers right now. This afternoon, there is a session about Kaggle competition. So Kaggle competition is basically, it's like a competition that usually people in the machine learning use. Is usually free, and sometimes it has actually a prize. And this afternoon, there is a talk about the Kaggle competition that we might have for space physics. We already had something like magnet and the data-driven model, and hopefully we have for the machine learning for the Kaggle as well. Another thing usefully placed is we have a committee that connects machine learning from GEM, CEDAR, and SHINE, and it's run by Matt Argel. So contact him. We have monthly meeting. You can come there, and then we talk about like about the fundings, about like, you know, opportunities in machine learning, about like, for example, this Kaggle competition. So if you're interested, please contact him. And also I want to advertise our session by me, Victor, and Joa, and we're going to have benchmarking of space weather forecasting models in AMS 18th conference this year. Please submit your abstract there if you are interested and attend. There are 3 machine learning sessions there, and I found them very useful. One last thing I want to tell you, if you're doing machine learning, always examine your data for pattern and biases. And this is like a Google AI failure example that confuses Chihuahua with muffins. And lastly, I want to thank everyone for the good discussion and for providing me the science that they were doing. And I want to finish my talk with another questions. Like we had a machine learning session on yesterday. Oh yes, it's already the day before yesterday. And we asked everyone, what is the difficult part of getting started with machine learning? And like skepticism about the result was the main one. And another thing was time commitment. So please let us know what is your problem. We might be able to help you. And I appreciate if you have questions, or I'm ready to answer. Thank you.
Thank you so much, Dr. Ferdousi. We have several questions in the chat, but we only have a few minutes. I'm going to ask just 1 to 2 questions, and we will move to the Slack channel for further discussion. So the first question is from Mikhail Sidnov. Is asking, most real data in space or in situ observation are little rather than big, very sparsely distributed, or just global indices. How do you suggest to adjust ANNs and all that to meet this little data challenge in heliophysics?
Yeah, I agree. This is like why I was saying we have lots of data, but we don't have high quality data. And so for these missions that we have, I think the methods that Andy was using might be useful, but for the future we might need like the missions that Larry Kepko is suggesting, having lots of satellites, so we have like better data. So now more than every time we need more data from the space, I think.
Thank you. And the second question is Riley Troller asking, with machine learning now being a separate field, do you see it as more productive for our field to have a basic understanding and collaborate with ML experts for the specifics, or to learn and implement these methods on our own?
Yeah, I totally agree. Actually, like if you, in our research communities, we are constantly working with machine learning experts and computer science experts, and the same thing is happening in the like FDL. They try to put everything together so we could learn from each other. We don't have to learn everything. We can just help each other. They need us too, because they have all this expertise and they are interested to apply their methods to the research that is really important, and space weather is one of their interests. And whenever we approach them, they are very open-minded and they're ready to help.
And the third question is saying that it's very hard upon seeing the results of the machine learning to be skeptical of its usefulness. However, is it possible that ML risks undermining the focus on scientific explanation of phenomenon as opposed to prediction? Might it in some cases obscure from view the physical causes of phenomenon which have been successfully predicted?
So let me read the question myself again. So it's like okay. For prediction always involve a black box? No, not necessarily. We do not have to have black box. I'm the fan of gray box, and I think we have to do most physics informed modeling. But for some cases, we cannot do. We can use like those black boxes but there are lots of gray boxes, and I think like for example for our FDL research, we did same things, and for Maria Elena's research, she did the same. And I think like another recent paper by Enrico Campriel, he has like another gray box example. Not necessarily we need always black box.
Yeah, so the last question is, what is the best approach to come up with standard community approved metrics?
Oh, that's a good question, actually. I think Mike Lohman had a great paper with Abby Azari about like, not having one single metrics, maybe for different, for for different domains, we could use different metrics. For example, for something, one other things I found useful is that another paper by Enrico, the gray box, that instead of using he uses the HSS score, instead of like just using for like one threshold, he goes over the stations and he have like a threshold of with percentage, like 95% confidence level, 70% confidence level. And those sort of things might be useful as well.
Thank you so much. And this is all of the questions we got. Thank you again for Dr. Ferdousi for your amazing talk. So I will go for Vania.
Thank you. Great discussions, and let's continue them also over Slack. And now we have another very interesting GSM tutorial, and I will let Elizabeth and Onyinye to introduce themselves and the speaker.
Hello, my name is Elizabeth Vandegriff. I'm a third-year grad student at the University of Texas at Arlington, and I'll be introducing our plenary speaker today, but I'll let my co-moderator introduce herself first. Onyinye, are you there? Doesn't look like Onyinye is.
Yeah, we seem to have lost her connection
right now. Okay.
So
right.
let's go ahead and hope that we can get in. And I don't know if somebody has a way to reach out to her outside of Zoom and see what's going on.
Okay, well, I can go ahead and introduce our next plenary speaker. Today's speaker will be Dr. K.Sorathia. Karim completed his PhD at the University of Maryland in Interdisciplinary Applied Mathematics and Scientific Computation program under the direction of astrophysicist Professor Christopher Reynolds. His doctoral and postdoctoral research involved developing and using large-scale supercomputer simulations to study turbulent transport in black hole accretion disks. Karim's more recent work has focused on space plasma physics modeling and theory at JHU APL. During his time there, he's acted as lead developer for Gamera, a global MHD code built to act as a successor to the LFM, and a test particle code CHIMP. He's used these tools to investigate interactions between mesoscale flow structures in global MHD and energetic particles, for example, Kelvin-Helmholtz magnetosphere losses, gradient trapping in particle injections into the inner magnetosphere, and the energization and deflection of cusp entering particles during northward IMF that contributes to dawn-dusk asymmetry in the formation of cold, dense plasma sheet. His current work is centered on leading the modeling team behind the comprehensive geospace model MAGE, Multi-Scale Atmosphere Geospace Environment, being developed by the Center for Geospace Storms. So let's welcome our speaker, Dr. Sorathia.
Thank you so much. Thank you so much for the very nice introduction, and thank you for inviting me to give a tutorial. It was only about 4 years ago, I think I attended GEM for the first time, and coming from a different field, I really didn't know very much at all about geospace modeling. So it was these tutorials that were incredibly valuable to learn. So I'm very excited and a bit nervous to give it a go myself. So let me save my bandwidth and share my screen. And unless I hear any objections, I'll assume everyone can see my screen and hear me okay. So today I'm going to talk about global modeling of mesoscale transport. And let me dive right in. To start at a very high level, we have this classical picture of magnetospheric convection as encapsulated by the Dungy cycle. Day-side field lines are open due to southward IMF and are transported over the poles where they reconnect the magnetotail and drive this earthward flow. That return flow moves seed particles that form the ring current radiation belts inwards onto stronger fields and shorter field lines, which results in Fermi betatron acceleration. And as they become increasingly energetic, their gradient and curvature drifts become more important, leading to these sorts of closed orbits. And while this isn't a very important global picture that we all probably have in our heads, we're also increasingly understanding that the images of magnetospheres that we see in textbooks and fashion magazines are fairly idealized. Real magnetospheres have curves. Or to put it another way, we see that magnetospheres in nature exhibit a great deal of structure on sort of these 1-ish RE scales. These are often referred to as mesoscales because of their separation from both the ion kinetic scale and the global scales of sort of tens to hundreds of REs. You can see here in this animation some examples of these kinds of mesoscale flow structures. Patchy and intermittent reconnection on the day side leads to flux transfer events. Shear flow along the magnetopause flanks creates Kelvin-Helmholtz vortices, which can play a role in the diffusive mechanisms by which solar wind plasma enters the magnetosphere. And finally, we see earthward convection from the tail in the form of these bursty bulk flows, or BBFs. And this is what I'm going to focus on in my talk here. I'll mainly focus on modeling this kind of transport, which requires capturing these mesoscale flow structures. Our understanding of magnetotail convection has come a long way, sort of becoming this story of bubbles, bursts, and buoyancy. We know from observations that earthward convection is bursty and localized with typical scales of hundreds of kilometers per second, sort of again 1-ish RE. Theoretical description of these flow bursts was provided by Pontius and Wolff, who identified them as bubbles, regions of depleted flux tube entropy, flux tube entropy being P times flux tube volume to the gamma, which move earthward due to interchange instability and the radially increasing flux tube entropy profiles that we typically see around Earth. You can see here on the right an example taken from the global simulation. This is showing the integrated flux tube entropy in the equator. And you can see these depleted bubbles being created due to azimuthally localized reconnection and then moving earthward, these sort of blue blobs. That's sort of this lava lamp looking picture with these blue blobs moving earthward. Above that is a schematic from an observational paper by Dubyagan demonstrating this sort of same kind of picture. And in that paper, Dubyagan found that the estimated flux tube entropy of these fast flows was a very good predictor of the penetration depth, consistent with this idea that these bubbles will move inward until they find a sort of equilibrium position based on their flux tube entropy. So why do we care about this kind of transport? These bubbles play an important role in transport across the transition region being the sort of bridge between the stretched magnetotail and the nearly dipolar inner magnetosphere. They carry dipolarizing flux and energetic particles. They're also associated with thermal anisotropy, which can provide free energy to the zoo of wave populations in the inner magnetosphere. And they also play a role in magnetosphere-ionosphere coupling via current closure, and potentially play a role in the substorm current wedge, which is still an enduring question. I'm showing here on the right a couple of simulations. The top is a global MHD simulation of a substorm event. The red-gray color is showing the non-dipolar component of the vertical magnetic field. So red is stronger than dipole, and black is weaker than dipole. And you can see here this sort of process of stretching and reconnection onset that eventually leads to the sort of launching of these BBFs with enhanced magnetic field towards Earth. Sort of continuing that picture here, I'm showing on the bottom right, test particle simulation where we seed a bunch of these test particles into one of these BBFs and then watch their subsequent evolution. Here I'm showing the particles themselves projected to the equator along the current field line and colored by their energy. And you can see sort of how these particles are injected into the inner magnetosphere and sort of fall onto these closed drift orbits. And I really like showing animations like these, not just because I think they look cool, although I hope they do, but also because I think these kinds of visualizations can give you a very visual and very visceral sense of the complexities of these kinds of interactions that can happen with these mesoscale flow structures. So how does the transport of energetic particles inside these flow channels happen? You can see here two cartoons of possible interactions. On the left, we have a convection surge, an enhanced electric field, but with more global sort of magnetic field structure. Here I'm showing the contours of constant magnetic field strength in white. In this case, we can envision a possible particle trajectory through this channel, shown here in magenta. And the particle is accelerated while in the channel, but its gradient and curvature drift will eventually leave it out. On the right, we have this much more intrinsically mesoscale kind of picture. Here we see a different kind of magnetic field structure with closed contours of magnetic field strength. We get these sorts of magnetic islands in these channels. And in this case, the gradient drift will trap the particle in the channel and allow it to be transported over a very large radial distance without sort of sneaking out the side. This can result in a significant amount of betatron acceleration as these particles get dragged into the inner magnetosphere and the much stronger fields that exist there. You can see this picture in a less cartoony way in this bottom right panel. This is from Yukorsky 2018, where they use MHD generated fields. And again, you can see the solid lines showing contours of constant magnetic field strength, where you again see these kinds of closed contours in these VBFs. And again, doing this sort of game, dropping test particles in there and following their subsequent evolution, where we can see that they very much do sort of stay in those channels as they get dragged into the inner magnetosphere. And that's not to say that this is the only possible mechanism, but just to illustrate an example. So in what I'm going to be talking about, I'll focus mainly on global modeling. But it's important to point out that in so much of our understanding comes from non-global simulations. Regional MHD, inner magnetosphere models, and PIC simulations allow us to really drill down into the critical details of these processes. They have been and will continue to be an important tool for building our understanding. But at the same time, there are certain kinds of questions that we can only answer with global modeling. Here I'm showing a diagram of how these mesoscale flow structures can play a role in the cross-system coupling and feedback of geospace as a whole. We can envision this causal chain that connects injections back into the magnetosphere, where injections lead to ionospheric currents, which leads to Joule heating, which leads to this broad latitude ionosphere-thermosphere response, which leads to feedback in the form of ionospheric conductance and potentially outflow. And so trying to understand the cross-system and cross-scale coupling that binds these constituent pieces of geospace together is a challenge where global modeling is really critical. So in these few overview slides, I've breezed over quite a lot. And luckily, there have been a lot of very fantastic surveys and overviews recently that can cover a lot of the background much better than I can. And so I highly recommend all of these tutorials and survey papers that have been very, very good recently. But for now, let me switch gears and talk about global and mesoscale geospace modeling. So one thing I was certainly surprised by coming from astrophysics into geospace modeling was just how much work we had left to do after finishing our MHD code. I'm showing here on the right one of these complex model coupling diagrams that makes everyone's eyes glaze over a bit, but it gives you a sense of the complexity of geospace modeling and all the different pieces that are critical to capture. Some of those major pieces are global MHD, a 3D fluid description of the global magnetosphere, inner magnetosphere model with a reduced spatial dimension, but 1 or 2 dimensions of the momentum space, an ionospheric electrodynamics model that uses field-aligned currents from the magnetosphere along with a conductance model to calculate the ionospheric electric field, which acts as, an inner boundary condition to the MHD. And also becoming increasingly critical is the importance of outflow models. I'll be talking about global modeling using our model MAGE for multi-scale atmospheric geospace environment. As an example, mostly because I wrote a lot of it, so I know how it works. Our first iteration of the MAGE model includes Gamera, RCM, and TiGCM, but this is definitely not the only geospace model. I'm listing some other ones here. And there's also been, again, a lot of these very good Monday magnetosphere seminars on several of these models. Most of these models are use sort of fluid descriptions of the global magnetosphere, and that's because fluid modeling is really efficient. You've only got 3 spatial dimensions and a handful of moments. But there are, of course, increasingly non-fluid approaches, including ANGI 3D and Vlasiator. So before talking about sort of mesoscale modeling, let me say a little bit more about the details of how we connect the global MHD to our inner magnetosphere model, which is particularly important for sort of capturing sort of BBFs. The animation here on the right is one of these sort of kitchen sink auto-generated videos that we have that we sort of run after our simulations, but it shows all the pieces involved in the global MHD and intermagnetosphere coupling. The panel on the right shows the meridional pressure with these two insets that show the MHD generated field-aligned currents. And the panel on the left shows the equatorial residual field, again, sort of the non-dipolar component of the field, with red being stronger than dipole, black being weaker than dipole. And the insets here showing the pressure that's coming from the RCM model with these two sort of blue squares just representing the same equatorial domain. In this case, we're projecting the pressure from RCM from the ionospheric grid to the equator. So like I said, this brings sort of all three of these pieces together. The ionospheric electrodynamics model, which we call REMIX, because the original LFM solver was called MIX. I'm pretty proud of that wordplay, by the way. The other pieces are Gamera for MHD and RCM for the intermagnetosphere. The basic trinity is that we use field line tracing in MHD to provide flux tube averaged plasma moments and flux tube volume. We provide flux tube volume to RCM. RCM has a 2D ionospheric grid plus an isotropic discretization of the energy space. It involves a series of 2D advection equations with the MHD provided boundary conditions and applies loss terms like charge exchange and other things. And finally, RCM returns density and pressure for MHD to ingest, and it also returns information about diffuse precipitation, which we use in our conductance model. One very important point to make is that RCM assumes a slow flow approximation, and MHD does not include gradient and curvature drifts. So the transition region that has both fast flows and important drift physics is really challenging for both of these models. Let me say a little bit more about some of the details of this coupling. One of the main pieces of all of this is that we want to alter the flux tube entropy in MHD to equal the one in RCM. And that connects both the pressure and the flux tube volume. The obvious way to do that is to change the MHD pressure. It's easier to hold a match to a flux tube than try to perform surgery on the field topology. But we did get a very good suggestion from Dick Wolf to estimate how the flux tube volume changes when we change the thermal pressure, particularly when the flux tube isn't very magnetically dominated. And this gives us a target pressure based on the average beta and also the MHD and RCM pressure. These agree in the low beta limit, but limit the pressure change and help with sort of these overshoots that we can get when we go into the higher beta transition region. In the earlier iteration of LFM RCM, we had an empirical plasmasphere model, but redoing things, we've added a zero energy RCM channel to represent the cold density that evolves dynamically based on the electrostatic potential. This is initialized with the Gallagher plasmasphere and refilled using an empirical Denton model, but is evolved dynamically from the same electrostatic potential. And you can see here on the right an animation of the MHD density, which includes the plasmaspheric contribution. And this is during the March 2013 storm. You can sort of see this kind of surge and then plume formation. I'm also showing here in the bottom row how we're using information from the RCM energetic electron channels to inform our diffuse precipitation. We can use information from the RCM electron loss model to calculate the precipitating number and energy flux, which we can apply to conductance. And there's lots of different loss models we can use, but one that I found particularly interesting is the one from the Chen 2019 paper, which includes empirical Hiss and Whistler wave power models that connect to the dynamically evolving cold density that we're modeling. So let me now take a second and say a little bit about why I'm talking about both global and mesoscale. So here I'm showing some simulations at different resolutions. Using our terminology, we go from sort of low to high resolution, double, quad, oct, and hex. And each one involves sort of doubling the resolution in each dimension, which for 3D simulation means that each step up is a factor of 16x in terms of the computational cost of the one before it. Here on the top right, I'm showing a very low res simulation of the Bastille Day storm and showing sort of this, qualitatively okay DST plot. But you can sort of see here, looking at the sort of equatorial slice, this is a very sort of poor simulation. And you probably don't see this image and think to yourself, I want to use this sort of old school Nintendo looking simulation to study something like how auroral streamers might actually connect to ground magnetic disturbances. So in this lower row, I'm showing a resolution study of different. This is showing the energy flux in the ionosphere using different resolution simulations on sort of a example from data on the right. And you can see that to capture certain scales of structure in the ionosphere, we really do need to probe down to these much higher resolutions. But remember, each jump is 16x, so these increases will start to add up. At the high end, we're sort of going from this sort of Nintendo simulation to our highest one. We're at about sort of a 4,000x difference in terms of the computational cost. And this highest resolution simulation costs about 100,000 core hours per model hour, which is not egregious by supercomputing standards, but is certainly by no means cheap. Let me show here another resolution comparison. This is a Gamera RCM simulation of an isolated substorm event, and I'm showing sort of two simulations, oct and hex resolution, with hex going to about 300 kilometer resolution in the central plasma sheet and about quarter degree by quarter degree resolution in the ionosphere. Let me start this over, and you can sort of see here in this panel that I'm showing in the bottom right, the green circle is sort of highlighting these ballooning interchange heads that we see only at this much higher resolution and not even at the oct resolution. And so again, we need to go to these high resolutions to capture a lot of these kinds of features. But there's also a catch, and this is one thing I'll come back to, is that we're kind of running out of runway. At this highest resolution, we're at 300 kilometers in the central plasma sheet, and that's comparable to the ion kinetic scale. And that means we're sort of pushing past the basic fluid approximation here. We can't really just dial up our resolution anymore without actually including sort of meaningfully new physics. So the point is that resolution matters, but resolution isn't just the number of cells on a grid. I'm showing here in the bottom left, this is one of these nice computational fluid dynamic test problems. This is a slotted cylinder that moves around in a circle and should come back to exactly where it starts. And next to that, I'm just showing the results. This is the same grid, but using slightly different details in the algorithm, in this case, using either a lower order reconstruction or the higher order, seventh order reconstruction we use in our MHD code. And again, you can see, even though the grids are the same, there is this meaningful difference in the behavior. And we actually find out that to get the lower order here to be as accurate as the higher order reconstruction requires about 8 times as many cells in each dimension. And that comes out to, again, a factor of 1,000 in terms of the total computational cost when we map that to 3 dimensions. So I know not everybody appreciates the elegant simplicity of the slotted cylinder test, but we can put this into a little bit more of a representative case. Let me start this video over. Here what we're doing is taking a given MHD state on the same grid, and we advance forward using either our standard algorithm on the bottom or a more diffusive advection algorithm in the top. And you can see that there's a very stark difference between the two of these, particularly when it comes to the kinds of mesoscale flow structures I mentioned, things like flux transfer events, Kelvin-Helmholtz vortices, and these bursty bulk flows. So what was the point of all that? Fluid modeling is easy, there's only a few spatial dimensions and a handful of moments, but also fluid modeling is hard. Even using sort of tailored geometry and these wide stencils, highly resolved fluid modeling is not cheap. So let me switch gears a little bit again. And now I want to talk a little bit about what we can and can't learn from a lot of these current global models. So global fluid models are good in that we can use them to create self-consistent bubbles over a long period of time. Here I'm showing some examples of this work. Kramer used OpenGGCM and RCM along with an event study, a series of events spanning several storm time DSTs, to show that bubbles are the primary transport mechanism outside of geosynchronous, confirming results that were previously sort of seen by Jian Yang using just RCM standalone. Here in the bottom left, I'm showing these sort of space-time diagrams. This is showing on the x-axis MLT with midnight in the center, and on the y-axis time. And these are taken at fixed L shell. I think they're both taken at 8 RE. From Kramer here on the bottom left, you can see the co-location of flow bursts and entropy minima. The max flow burst is shown in the colored circle, and the location of the entropy minimum is shown in the sort of black marker, and you can see sort of how they're co-located to demonstrate the importance of these sort of bubbles. There's also been work showing the critical role of bubbles in dipolarization. Here you can see next to that in Merkin 19's work, a plot of BZ and how these azimuthally localized bundles of flux are solely responsible for the global dipolarization that's observed in the simulation. In fact, up here I'm showing in the top right, oops, sorry. This is a Gamera RCM simulation of the same event that Merkin 2019 looked at. This is showing in the inner magnetosphere. This is red is BZ, this is BZ. And you can see that right around the onset at 920, this region of red will dramatically expand this global dipolarization. And it's precisely because of these sort of localized flow bursts that carry the magnetic flux. So we can use these fluid plus inner magnetosphere models to see the critical role of bubbles in transporting flux and plasma to the inner magnetosphere. But there are important limitations. These models don't have a fully self-consistent transition region. We're combining sort of a slow flow with drift physics model using inner magnetosphere to the global MHD model, which doesn't have drift physics. We're missing ion kinetic effects like thin current sheets, likely play an important role in substorm onset. These models don't necessarily capture pressure anisotropy or wave acceleration. But again, even with these limitations, these kinds of models can demonstrate the importance of bubbles to transport. This is some work in which we wanted to focus more on the length scales of these bubbles and how energetic particles interact with those length scales. This is an extension of work done by Yukorsky in 2018, where they seeded test particles into a single bursty bulk flow. Here we stream test particles into this blue arc here on the night side, and we weight them to match the MHD moments. So we're basically using the MHD density and pressure at the instant that the test particle is created. So we're essentially creating this sort of test particle mirror of the MHD flow. What I'm showing here on the right, test particles are projected to the equator, colored by their energy, and the size of the marker represents the weight. So the weight is just the number of real particles that each test particle is a proxy for. And there's a big caveat here, of course, that these are test particles. There's no feedback from these particles to the larger flow. So what we want to do here is study how the flow structures actually move test particle energy around. To do that, we want to connect the equatorial movement of test particle energy to the ambient MHD flow. For the test particles, we do that by periodically projecting their 3D location to the equator and looking at the radial velocity of that equatorial projection. For the background flow, we do that in two ways. We look at the magnetic length scale, sort of B over grad B, just sort of a quick way to put together a length scale. What I'll also call the relative buoyancy, the sort of flux tube entropy, fractional deviation of the local flux tube entropy from this time averaged background. And I'm showing that here on the right, where blue corresponds to negative, meaning bubbles, and red corresponds to blobs, meaning sort of overfilled compared to the background. And you can see sort of how this quantity, sort of these blue regions sort of lighting up in these bubbles, and also sort of how in front of a lot of these bubbles, we get the formation of these red regions, sort of these bubble-driven blobs that we're also seeing in Yang 2011 with RCM. So doing all of this, we get this collection of data points connecting the equatorial motion of test particles to the MHD flow properties. And when the dust settles, we get about 1 billion or so data points that we can play some statistical games with. For this next part, there's some fiddly details I won't go into a full sort of explanation of, but I'm happy to answer questions about. But basically, we have this set of 1 billion points and connecting the test particle motion to the MHD flow. We want to consider the difference between the occurrence rate of certain properties and basically how often do these bubbles occur statistically versus what fraction of the transport do they represent. And I'm showing that sort of in these 3 different regions, sort of any bubble, meaning any amount of depletion, sort of slightly more depletion, versus going all the way down to this much more deeply depleted bubbles. And what we see in each of these cases, of course, that bubbles punch above their weight. They move more content than they represent in the total sort of statistics. And in particular for these deeply depleted bubbles, they carry about 1/3 of the total content, even though they only make up about a few percent of the statistics. We can look at this data in other ways. For instance, we can look at the length scales associated with the bubbles, shown here in the top right. We find that these bubbles are mesoscale, with length scales sort of peaking at about 1 to 2 RE. And that most of these bubbles, sort of 80% of them, fall into this range of about 0.5 to 3 RE.
You have about 5 minutes left.
Ooh, let's see. Okay, so let me just skim over this part a little bit, and I'll just say that we can show that the particles that carry this energy are generally more energetic, sort of in the 20-ish keV range, and that means that they're going to have drift, sort of gradient drifts that are comparable to E cross B flow, which again means we need both drift physics and fast flows. And that also means that MHD and RCM are both insufficient here. You can also see that another resolution comparison, that in this range of sort of these mesoscale flow structures, we get a very significant difference going from the lowest to higher resolution. Finally, we also see that bubbles are unavoidably kinetic. There's been a lot of good work by Yulin and her group using global hybrid with Angie3D. And they've been able to look at the sort of self-consistent formation of bubbles. One thing shows that, these bubbles are characterized by anisotropic pressure that's not constant along the field line, which means that most of these global inner magnetosphere models are not valid there. And they also find that there's important non-MHD waves like kinetic Alfvén waves, where the parallel electric field can play an important role in particle acceleration. But of course, these are computationally very demanding. Typical simulations are several hours, whereas important geospace effects like storms are several days. Let me try to skip a little bit here, but the next main point, I think, is how do we validate these kinds of mesoscale flows? How do we look at bubbles and models versus data? Virtual spacecraft simulations may not tell us very much. We don't necessarily expect to reproduce every wiggle in our model that we see in the data in the exact same place. And so sort of a more robust way to do that is think about this in terms of statistical comparisons. And this is showing sort of very nice, what I thought was a very nice example in Whitberger 2015, where they derive sort of BBF statistics to construct a superposed epoch analysis from their simulation in a similar way to the GeoTail superposed epoch analysis conducted by Otani in 2004. And you can use models like this to show that there's, some kind of qualitative agreement, even though, we don't necessarily see a huge amount of quantitative agreement in this yet. I'll go ahead and just skip this here. And basically just jump to the point though, how do we do a better job making these kinds of mesoscale validation? And the short answer is that we need more mesoscale data to compare to. You can see here some examples of recent work that tries to address some of this by Drew Turner and Amy Kesey. But as Larry Tepko pointed out earlier in the week, there's this big mesoscale data gap to overcome. The obvious solution is more missions, constellations like MagCon, and more ENA imaging. And at the same time, there's evolving new ways to make use of the data, using sort of that kind of data to train this data mining machine learning models. I'm showing here on the bottom right, sort of an example of that using Grant Stevens' work with SST compared to a model simulation of the same event. And there's also advancing work on information theory, where we can imagine comparing the information flow of the variables in our model to that derived from data. And I think sort of these new tools combined with more mesoscale data can really get us at the core question of, will we learn the same thing from models that we do from data? So let's see, that was all pretty long-winded, but the point is bubbles matter, they're hard to resolve and validate, and they're unavoidably ion kinetic. So I think this is going to be my wrapping up. So what's next? We've all heard these many discussions surrounding beyond MHD, and we're seeing lots of different approaches being pursued. I talked about the work on global hybrid being done by NG3D. There's also Vlasov type codes, which directly solve the Vlasov equation. This includes Vlasiator, but also the spectral code SPS being developed by folks at Los Alamos. We've seen approaches like embedded PIC. There's also been interesting work in the realm of combining a partial fluid and partial particle description of the plasma, like the approach of K-Global. I'm personally, I know, very interested in this approach, but as a guy who has written both a fluid and a particle code, I might be a bit biased. There's been work on higher order moments, like the 10 moment model being used in Jekyll, or these kinds of very different methods like empirical reconstruction and data mining. So we've got lots of promising options, but this is still a very hard problem. Geospace is big. You need ion kinetic physics, but also highly resolved dynamic range spanning sort of 100 RE to sort of, ion kinetic scales. In addition to simultaneously resolving that spatial range of scales, we also have to capture fairly long periods of time. Important geospace things happen over several days, like geomagnetic storms or the formation of a cold dense plasma sheet. And recall that even these highly resolved fluid simulations can get, reasonably expensive. But we've got technology on the way to help us. We've got the first generation of massive exascale supercomputers coming online, which offer us this sort of unprecedented computational capability if we can figure out how to use them. We have this sort of challenge of figuring out how to run increasingly complex models on increasingly complex hardware at increasing scale. And then after all of that, we need to figure out how to learn from data at this scale. It's easy for a simulation to produce a terabyte of model data. And after running that simulation, we still need to figure out how to turn just that, mess of numbers into scientific intuition. So what's next? I think the correct and boring answer, it depends on the application. We should pursue all of the above and so on. But it's the last day of a long week, so I'll go ahead and take my own swing at it. I'm a big fan of elastic approaches, methods where we can adapt how kinetic the description is, either up or down in different regions and times, and methods that allow us to augment a fluid description instead of trying to completely replace it. So I've just tried to tell you why there's a whole bunch of really hard challenges on the horizon for global modeling. And I think that's great. That means there's lots of opportunities to find clever solutions to those problems. There's this joke about may you live in interesting times being a curse, but I'd say that the alternative is far worse. So my message for students is that it's a great time to be a modeler. And also, not for nothing, developing these kinds of skills will give you lots of career opportunities if you decide to pursue other non-science options later. And I think I did go over, so I apologize. But that is it for me.
Thank you so much, Dr. Karim, for the great talk. Thank you. My name is Onyinye Nwankwo. I'm a first-year PhD student at the University of Michigan, and I'll be handling the Q&A section. So the first question here is from Bill Lopko. Says, do the simulations provide any insight into what determines the cross-tail length scale, few radius of the flow burst?
That is a very good question. I don't know the answer to that offhand, but I think that is a very important question to answer. And there does seem to be a fair amount of sort of resolution consistency when you go high enough. So I think there is probably an answer lurking there somehow, but I admit I do not know what it is off the top of my head.
Okay, great. The next question is from anonymous attendee. He is like, or she is like, how important is to resolve mesoscale numerically in MHD in order to get large-scale convection right? This is a long-standing problem for Earth-ocean models.
I guess it depends on your definition of right. I think that we could probably get certain behavior. I showed this very low resolution simulation that got a lot of sort of global details correct. But it's hard to imagine that that's going to tell you, again, very specific things about the MI coupling, maybe, specific sort of regions in the ionosphere, localized details. And also even not just sort of spatial resolutions, but I also suspect energy resolutions, sort of, are we getting the ring current energetics, right? Are we getting sort of the ring current properly, the sort of right energy spectrum in the ring current, which is going to significantly affect sort of the timescales of recovery, because things like charge exchange are going to be very dependent on that energy spectra.
Oh, great. Thank you, Dr. Karim. The next question is from Jason Deere. He says, suppose we have one region where multiple phenomena are occurring, some of which necessitate a guidance-centered treatment, and some of which require an MHD treatment. Do you have thoughts about how we might best integrate both treatments in the same region in a global model?
Oh, yeah, I have lots of thoughts. This is, again, I think, a place where the approach in K-Global is very interesting, where you can basically have sort of a main fluid distribution. You can sort of, I guess the way I would think about it is you sort of have your distribution function and you have a fluid description of the thermal part of it, but you could then also have, say, a particle component that's not representing the entire ion population like it would in global hybrid, but only using particles to represent the sort of non-thermal tail, where the guiding center stuff is going to be the most important. And potentially even, you could do that with a full Lorentz description of it if non-adiabatic effects were important.
All right, thank you so much. I think this is the last question you'll be answering for us. We'll have to move the other questions over to Slack channel, and we'll be able to continue from there. Thank you so much.
Thank you.
Thank you all. I hope you can hear me. I have some very brief closing remarks. So I hope you could stay for a few more minutes with us. Let's see. Okay, so I hope everyone sees my screen. So I would like to thank you all for participating and making another very inspirational virtual GEM workshop. So we had more than 500 people registered and more than 200 students. And from the responses, about 60% prefer to be named as he or him, 33% as she or her, and 8% to use their name. And 22% consider themselves as part of an underrepresented group in STEM. So we also had 144 posters and several special activities presented in Gather Town. And I would like to note that the tutorials, presentations, Zoom recordings are available at the virtual GEM workshop page, as well as we have posted now there the results from the mental health quiz and the presentations on team dynamics and mental health awareness from Dr. Vertesi and Dr. Macmillan, respectively. So you can review those and look for answers to many questions you may have. So several members of the steering committee are ending their terms this year. So we would like to express our special thanks for their outstanding service to the community. And these are Martina Hulidu, Seth Claude Pierre, Shino Tani, and our student representative, Agnit Mukhopadhyay. So we will be looking for 3 new research area coordinators in the fall. And Agnit, do we know name of the new student representative?
Yes, Vania, thank you so much for the cue. We just concluded our student representative elections at 11 a.m. today. My biggest thanks to my fellow student representative Mei-Yun for helping organize the election polling and making the whole process as public and transparent as possible. Our larger thanks to the two nominees who came up and nominated themselves for the position of student rep. By a margin of 6 votes, we have the new student representative for GEM is Miss Elizabeth Vandegriff, and I am as I am outgoing, Elizabeth will be introduced into the steering committee from today onwards. So congratulations, Elizabeth. Thank you so much, Vania.
Okay, thank you. Congratulations, Elizabeth. And we also would like to thank our student moderators, designers, for their great help. We couldn't do the virtual GEM without them. I also would like to let you aware that there are 3 focus groups that are ending in the fall, and the steering committee will issue a call for new focus groups via the GEM newsletter. So please subscribe to the newsletter to see all updates. The guidelines are given in the GEM bylaws on the GEM wiki. And also I would like to emphasize that although the focus groups proposals need to choose a primary research area, they don't have to tie all their science to that research area, and we very much encourage proposals that are addressing the bigger system science questions. So today we have concurrent sessions in the afternoon, and then we will have a social hour. So please join us first via Zoom. We will try to take some group photos, and then we will move to gather town to the beach area for more chatting, browsing, photo collections, and maybe more pictures. So the opportunity to communicate will remain open after the workshop. So the VGEM virtual platform, the Gather Town, will be available for the next 2 weeks. So you may go and look at the posters that you have missed, and please continue the discussion via the Slack workspace. Also, the meeting organizers are preparing a participant survey. So please take the survey when you receive it and send us your feedback on how we could improve future GEM meetings. So I would like to thank also our support team, Gather Town designers, Esther Chen, website extraordinary Greta Gabois, website support Kathy Whitman, UNH IT support by Andy Dove, and Umbe as our meeting coordinator. Thank you very much. We couldn't do this workshop without your help. And I know we are all looking forward to meet in person, and let's hope this will happen next year when we will have a joint back-to-back summer workshop with Shine in Hawaii, and you can see more information on the wiki page. We are discussing plans for the mini GEM, and we will announce them through the newsletter as soon as they get finalized. And finally, the big question everybody is waiting for, the results for the new GEM logo contest. So we received 166 responses, and we do have a winner. So here is the winning logo, and please start using it in your next presentations and publications. And now I will turn it to the meeting organizers to select the winner of the gift card. So let me try to stop sharing my screen. Okay, so Chailin.
Thank you, Vania. First, we want to thank people who submitted their creations. They're all amazing. And thank you everyone for casting their votes. We have entered all 166 names in this wheel. If you zoom in carefully, you should be able to find your name. Okay, now, who is the lucky one to win an Amazon gift card? Ready? Go. The winner is Jen Coyle. Congratulations. You will receive your prize in the email. Thank you, everyone. We'll see you in the breakout sessions.
Thank you all. And with this, we conclude the plenary session for VGEM 2021. So please join us at the social hour in this afternoon. Bye for now.
See you in Hawaii.